Welcome to this video session. Today I'm going to talk about a problem related to authentication when we are using AES, for example, in CBC mode. During the previous session, I talked about encrypting the plain text using AES and then making sure that the ciphertext is not modified by signing the ciphertext using a MAC key. But I made a mistake deliberately, and I was talking about a buggy version of encrypt followed by authentication. There I missed an important problem in that I didn't cover the IV as part of the MAC. So the MAC was computed purely based on the ciphertext, and we didn't talk about covering the IV. So the idea now is that we wanted to be able to protect against tampering of IV as well. So what happens if we don't protect the IV? Well, something really bad happens. So you can modify the first bytes of IV and have a controlled effect when the ciphertext is decrypted. So very quickly, I'll summarize the flow. We had this enc followed by auth step, meaning first we do compute the ciphertext, right, by encrypting the plain text with the key K, right, and then we compute the MAC by using a MAC key. How did we compute MAC? For example, in our case, we did HMAC of MAC key, right? We need a MAC key, and we feed in the ciphertext. This looks almost correct, but it was buggy because we forgot the IV. So in this session, I'm going to talk about how to do it properly so we don't get into the problem of IV tampering. Okay. So let's look into the let's look at the code now. So here is our data encryption key, and then we derive a MAC key from the data encryption key. If you prefer to generate a separate MAC key, that's perfectly fine, or you may use a HDF, so-called key derivation functions that we talked about in other presentations. So from your data encryption key, you could derive a MAC key. That's not a problem. And then you would generate an IV for each message, right? That's basically a random number. I'm using a random IV for each message. And then we go ahead and encrypt the plain text using the data encryption key and the IV. And then we compute the MAC of the ciphertext. We send the IV, the ciphertext, and the MAC to the receiver. The receiver will verify the MAC by taking the ciphertext, MAC, and the MAC key as input. Of course, the sender and the receiver must have the same data encryption key. Otherwise, the receiver won't be able to decrypt the data, right? If of course, the sender and the receiver must agree on how to generate the MAC key from the data encryption key. That's the prerequisite, anyways. All right, this particular setup looks very harmless at the first look. However, there is a serious problem. Let me first show you, just compile this. I'm going to compile this now first and run it and show you whether everything works perfectly or not. Okay, so here is our IV, here is the ciphertext, and this is the MAC. So we sent these three things to the receiver. The receiver and the sender already agreed upon the key, so they have no problems in exchanging the key. That's the assumption. The MAC status is true, and the plain text is AAA. That's what the sender sent. But let's look at the problem now. What happens if I edit the IV? That's something that we talked about earlier. Let's do it very quickly so that we recall. So let's just change the IV here, right? IV of say 0 is equal to say 0, 0, right? Let's see what happens now. Now you may notice that the first character is corrupted. When the receiver decrypts the first character, it's corrupted. When the receiver decrypts the first block, the first byte is corrupted. But the MAC status is surprisingly true. That's because the MAC algorithm was not considering the IV as part of the analysis. Okay, so what shall we do now? Very quickly, we can fix the problem. What we are going to do is simple. We will be adding the IV as part of the MAC calculation. So something like this. I'm going to take my ciphertext and append IV to it. Okay, so I'm doing something like this. IV followed by ciphertext. Append is basically just put them together, right? And now, of course, during the verification also, we need to use the same append function. Append is basically a small utility function that takes 2 byte arrays and concatenates them together, and that's basically what append is doing. So once you have the IV and the ciphertext appended, let's verify this. Let's make sure it works. Okay, yep, it works. The status is true. There's nothing wrong. What about the scenario that if I modify the IV, what happens? Let me modify the IV after the MAC is calculated, and we are sending that to the receiver, right? Somebody modified it, man in the middle or something like that. So let's see. Now, hopefully the MAC verification algorithm fails now. We can check that part quickly. Yep, you see here, the MAC status is false, MAC verification failed. Therefore, the receiver is not even accepting your ciphertext. Okay, so this is the encrypt-then-authenticate scheme. This is the scheme recommended. All we did is simple. Let me summarize at a high level. We basically calculated the MAC, but the MAC is now considering the IV as well as the ciphertext. Okay, so MAC is, as you can see, MAC is derived from ciphertext and IV together. So if I tamper the IV or the ciphertext, the MAC verification algorithm is detecting that problem. So let me show you first. Okay, this is the right way to do it. Okay, and let me show you what happens if I just ignore the IV and do something more severe damage. Okay, let's do that quickly. I have written this little notes for me. I will use that line of code. So I'm going to change the resulting plain text in a controlled way. Let's assume I am the man in the middle, and I know that the first block of plain text is bunch of A's. I want the decryptor to not show a bunch of A's. I want the decryptor to get this message instead. Okay, that's what I'm going to show now. All I'm doing is modifying the IV in an interesting way. I will show you the routine of modify IV in a moment. So let's get back here. Let's inject this code. Let's assume a man in the middle is modifying our ciphertext. Okay, what is he doing now? He knows the IV because it's sent in plain text, and he knows let's assume he also knows the plain text. Okay, the first block of plain text. But now he's going to have a controlled effect. He wants the decryptor to get this message. Don't forget IV is the message he wants to send out. Okay, so how can he do that? If you look at the modify IV program, all it does is it takes the IV and the known plain text and the desired plain text, and it uses the properties of IV. So what we are trying to do is that from the way the CBC mode works, in this case this is CBC based, by the way, this is CBC algorithm. We know that first we encrypt the plain text using simple XOR of the plain text block with the previous ciphertext block. So that means if we have only 2 blocks, say the IV block and then the ciphertext block, okay, something like this is happening. Let me write it for you. So what we are doing really is that we take the IV, right, and we XOR it with the first block of plain text of 0. I mean to say the first block of plain text, right? These two things are XORed first, and then we encrypt using the key K, right, to produce the first block of ciphertext. Okay, this is what we do. We produce the first block of ciphertext by this process. So now during the decryption process, we get the plain text by taking of course, applying the decryption algorithm on the key K, and then we do ciphertext of 0, right? And then we XOR it with IV to get rid of IV, because IV is what is coming out of this. What is coming out of this is basically IV followed by plain text of 0. So we cancel out the IV and IV. So I can show why this is plain text. The reason is this. What we get out from the decryption algorithm is this, and then we have the other IV. So it IV and IV will cancel out. We get the plain text of 0. So that's that's how the CBC mode of encryption and decryption works. So now, from this picture, we can map it to this part. Okay, why did I do this way? The reason I did it this way is that now I take the original IV and I take the known plain text, I XOR it together, and I also XOR it with the desired plain text to form a new IV. So I'm forming a new IV here, essentially. I form a new IV here. When the decryptor is using my new IV, the old IV and the old plain text will cancel out, and the attacker will be able to send successfully the desired plain text. That's basically the idea. Okay, so let's get this up and running quickly. Java say, okay, let's see whether the algorithm, the attack algorithm works. Okay, aha, you see here, don't forget IV was the message the receiver got. And MAC verification also is true because we didn't include the IV. So you want to be careful when you use authenticated encryption. The IV must be part of your MAC calculation. Otherwise, IV can be modified. So I'm going to just fix this problem very quickly. Okay, so all we have to do is append the IV to the ciphertext. Okay, and then it doesn't matter whether you put the ciphertext first or the IV next, whatever, because we are basically taking the whole ciphertext anyways and then applying a MAC. So in this case, the order should not matter. Append, but of course it has to be the same order. If I put IV ciphertext during the MAC calculation, the MAC verification should also have the same order. Okay, I mean this order here has to be exactly the same here. Okay, let's try this now quickly. Yep, MAC verification status is true, and the receiver got the plain text that was sent by the sender. Okay, so to sum up, what you wanted to do is first encrypt your plain text, right? That's what you do here, encrypt. Get the ciphertext, and then apply HMAC on the ciphertext. Of course, you should consider the IV as part of the ciphertext now. And then during the verification, first verify whether the received IV ciphertext matches the MAC the sender sent using the MAC key. And if the verification is good, then go ahead and decrypt it. This is called the Encrypt-then-Authenticate scheme. So what we are talking today is how to fix the encrypt authentication scheme problem we talked earlier. Of course, you may want to use something like GCM or CCM because it has built-in capability to introduce authentication, so you don't have to manually write extra code like the way we did it today. You know, we appended the IV to the ciphertext and so on. There's a little bit of code there, of course, but if you can't use GCM or CCM for whatever reason, then this is a perfectly fine approach. Sort of have one data encryption key and derive a MAC key and apply encryption of the plain text first, calculate the MAC, use the IV also as part of the MAC calculation. Now MAC is computed on the ciphertext, okay? Only if the MAC is successful, you go ahead and decrypt it during the decryption time. Okay, that's all. Thank you very much.